Imagine grasping a single grain of sand, an almost imperceptible speck. Now, envision that same tiny volume holding the crushing weight of an entire fleet of battleships, anchored to the fabric of reality itself. Everything you thought you knew about solidity, about what constitutes heavy, is about to be utterly redefined. This isn't just dense, it's a cosmic anomaly so extreme it forces us to confront the very limits of matter, challenging our intuitive grasp of physical existence. Picture Mount Everest, its colossal granite mass, compressed down to the size of a sugar cube. Yet, even that mind-bending comparison falls drastically short of true cosmic extremes. A single teaspoon of the universe's densest substance would weigh more than every car, truck and airplane on Earth combined. A gravitational singularity in miniature. Today, we embark on a journey to the heart of collapsed stars, exploring the impossible physics that forge neutron stars. Prepare to witness a reality stranger than even the most imaginative fiction. If the profound, often terrifying mysteries of the cosmos ignite your curiosity, hit that like button and subscribe. Join us as we plunge into the ultimate extreme. Prepare yourselves, we begin. The journey to understanding matter so impossibly dense begins not in the cold vacuum of space, but in the fiery hearts of truly colossal stars. These are not our sun's modest kin. We speak of celestial titans, stars born with initial masses often 10 to 100 times greater than our own star. For millions of years they blaze across the cosmic canvas, incandescent behemoths fueled by an internal furnace of extraordinary power. Their lives are short, intense spectacles, burning through hydrogen fuel at rates that dwarf stellar processes in smaller suns. This furious consumption is the engine of their brilliance, but also the harbinger of their ultimate cataclysmic end. Deep within the core of such a massive star, the conditions are beyond anything we can conceivably replicate on Earth. Temperatures soar to hundreds of millions of degrees, creating a plasma where atomic nuclei are stripped of their electrons, a swirling maelstrom of fundamental particles. Here, nuclear fusion is the dominant force, a cosmic alchemy that transmutes lighter elements into progressively heavier ones. Hydrogen fuses into helium, helium into carbon, and carbon into oxygen. Each step in this elemental cascade releases immense energy, momentarily counteracting the crushing inward pull of gravity. It is a delicate, ferocious balance, an eternal tug-of-war between the force seeking to collapse the star and the outward pressure generated by the continuous nuclear reactions. The energy liberated by fusion acts as a powerful internal explosion, constantly pushing against the star's own immense weight. As the star ages, layers of progressively heavier elements form around its core. Like the skins of an onion, silicon fuses into sulfur, then argon, calcium, titanium, and finally, nickel and iron. This process, governed by the stellar fusion cycle, represents the star's last desperate act of creation. It is a monumental feat of stellar engineering, constructing a core of pure iron. But here lies the profound, inescapable problem. Iron is a nuclear dead end. Unlike lighter elements, fusing iron consumes energy rather than releasing it. It's like trying to burn ash in a furnace that demands fuel. Once a significant iron core accumulates, typically reaching a mass of about 1.4 times that of our Sun, a critical threshold known as the Chandrasekhar limit, the star is in existential peril. It has exhausted its viable fuel source for outward pressure, leaving gravity unopposed and poised to claim its ultimate victory. The formation of this iron core signals the star's imminent doom. With no energy generation to support it, the core begins to collapse. This isn't a slow, gentle settling. It's an instantaneous runaway implosion. In a mere fraction of a second, a core larger than Earth can shrink to a sphere just tens of kilometers across. The speed of this collapse is staggering, approaching a quarter of the speed of light. Imagine the unimaginable scale of a planetary mass, compressed with such ferocious, unyielding speed that the very atoms within it are shattered, their fundamental structure obliterated by the relentless gravitational vice. The forces involved make even the most powerful terrestrial explosions seem like a gentle whisper. As the collapse accelerates, the density within the core reaches levels that utterly defy terrestrial experience. Electrons, normally orbiting atomic nuclei, are squeezed with such force that their individual quantum identities begin to break down. The Pauli exclusion principle, a fundamental rule of quantum mechanics that forbids two identical fermions from occupying the same quantum state simultaneously, provides a temporary desperate resistance. This electron degeneracy pressure is the quantum force that supports white dwarf stars, preventing their further collapse. But in the core of a massive dying star, even this quantum standoff is overwhelmed. The gravitational vice is too powerful, the inward pressure too immense. The very fabric of subatomic existence begins to warp. The electrons, unable to resist further compression, are violently driven into the protons within the atomic nuclei. This harrowing process, known as inverse beta decay or neutronization, transforms protons and electrons directly into neutrons, simultaneously releasing a torrent of neutrinos. These ghostly particles, nearly massless and interacting only weakly with matter, stream away, carrying vast amounts of energy with them and accelerating the core's cooling and collapse. The core effectively becomes a giant atomic nucleus, a super-dense soup of neutrons. The vast empty space that once housed individual atoms with their extensive electron shells utterly vanishes, replaced by a substance where matter is packed shoulder to shoulder with no empty volume left. It is a fundamental transformation of matter itself, a transition to an exotic state, occurring on a scale that beggars belief. This rapid neutronization and compression continue until the core reaches an astounding density. A single cubic centimetre of this material would weigh more than every human being on Earth combined. To put it another way, if you could take all the people on our planet and condense them into a volume the size of a sugar cube, you'd begin to approach the density of this nascent core. At this point, another quantum force, a neutron degeneracy pressure, finally asserts itself. Neutrons, like electrons, are fermions, and they too resist being forced into the same quantum states. This immensely powerful force, combined with the strong nuclear force that repels neutrons at extremely close quarters, brings the implosion to a screeching, violent halt. The collapsing core suddenly becomes incompressible, rigid beyond imagination, acting like a cosmic brick wall. The halt is not gentle, it is a rebound, an explosive bounce. The infalling outer layers of the star, still plummeting inward at incredible speeds, crash into this newly formed super-dense neutron core. The impact generates a colossal shockwave that propagates outward, blasting through the star's remaining layers. This is the genesis of one of the universe's most brilliant and violent phenomena, a Type II supernova. For a brief, dazzling period, the exploding star outshines an entire galaxy, radiating as much energy in a few weeks as our Sun will produce in its entire 10 billion year lifespan. This cosmic cataclysm scatters newly forged heavy elements across vast cosmic distances. These elements, including carbon, oxygen, nitrogen, and even gold and uranium, become the fundamental building blocks for future stars, planets, and perhaps even life. Our very existence, composed of these elements, is a direct consequence of such stellar violence. It is a spectacular and terrifying process, a grand recycling event on a cosmic scale. But what remains after this cosmic farewell? Amidst the expanding nebula of gas and dust, a tiny, incredibly dense remnant is left behind, a neutron star. It is the collapsed core, now stripped of its outer gaseous envelopes, a pulsating monument to extreme physics. This nascent neutron star is often still incredibly hot, millions of degrees, and spinning rapidly, its magnetic field amplified to an intensity trillions of times stronger than Earth's. It is here, in this stellar corpse, that we find the matter we seek to understand, the densest known stable substance in the cosmos. Its formation is a testament to gravity's relentless power, capable of forging such an exotic state of matter from the ashes of a once glorious star. Understanding this stellar demise is crucial, for it sets the stage for the true horror and wonder of a single teaspoon of neutron star matter. The extreme conditions of its birth dictate the unimaginable properties we are about to explore. The sheer energy involved in neutron star formation surpasses even the Sun's entire lifetime output in mere seconds, a fleeting cosmic hammer blow that forges the ultimate condensed matter. This process, a Type II supernova, is not just a stellar death, it's a universe-shaping event, distributing the elemental ingredients for future worlds and leaving behind a monument to quantum gravity, a cosmic heart of pure nuclear density. This final, compact core, barely 20 kilometers across, represents the ultimate triumph of gravity over all other known forces, creating a realm where the very laws of physics are pushed to their most profound limits. The fiery stellar cataclysm of a supernova leaves behind a remnant unlike anything else in the cosmos, a celestial body that pushes the very fabric of matter to its theoretical limits. This is the neutron star, and its essence is a substance so extraordinarily compressed, so profoundly dense, that it demands a complete recalibration of our understanding of solidity. At its core lies what scientists informally refer to as neutronium, a state of matter where the familiar structure of atoms has been utterly annihilated, replaced by a homogeneous, incompressible sea of neutrons. To truly grasp the concept of neutronium, we must shed our terrestrial notions of density. Imagine, if you will, taking a colossal celestial body, say, our own Sun, which itself contains over 330,000 times the mass of Earth. Now, picture that entire solar mass compressed into a sphere barely 20 kilometers across, the size of a modest city, perhaps Manhattan or London. This is the scale we're talking about. Within that unbelievably small volume, the Sun's entire mass is crammed. The implications of such compression are staggering. If you were to take just a single sugar cube of this material, an object so small it could rest comfortably on your fingertip, its mass would be unfathomable by human standards. That humble sugar cube would weigh more than 3 billion metric tons. To offer another analogy, imagine every single car, truck, bus, train and airplane currently operating on our planet, their collective bulk brought together. A mere teaspoon of neutron star matter would outweigh them all, an entire global transportation infrastructure reduced to a cosmic speck. It is a mass so extreme, concentrated into such an infinitesimal volume, that it warps space-time around it with ferocious intensity. This hyperdensity is not merely a theoretical construct, it is a direct consequence of the catastrophic gravitational collapse described in the previous block. When electron degeneracy pressure, the quantum force supporting white dwarfs, is finally overcome, electrons are forced into protons, forming neutrons and neutrinos. This process, known as neutronization, strips away all the empty space that makes up the vast majority of an atom. Atoms are, surprisingly, mostly empty space. If an atomic nucleus were the size of a pea, its electrons would orbit kilometers away. In a neutron star, all that void is gone. The neutrons are packed together so tightly that they are, in essence, touching. The strong nuclear force, the very force that binds quarks within protons and neutrons and holds atomic nuclei together, now dictates the macrostructure of this exotic star. It is the ultimate expression of nuclear density, a giant atomic nucleus on a stellar scale. The internal structure of a neutron star is a layered symphony of extreme physics, a journey from relative familiarity to the truly bizarre. The outermost layer, sometimes called the outer crust, is still incredibly dense by Earth standards, millions of times denser than lead. Here, gravity is so immense that even atoms are crushed into a crystalline lattice of heavy, neutron-rich nuclei, bathed in a sea of relativistic electrons. While these nuclei retain their identity, they are far from the stable forms we know. They are atoms under duress, their electron shells squeezed to unimaginable extremes. This crust, though only a few hundred meters thick, is thought to be incredibly rigid and smooth, far smoother than any planetary surface, with irregularities no larger than a few millimeters. Beneath the outer crust lies the inner crust, a region where the pressure becomes so intense that the nuclei themselves begin to dissolve. As protons and electrons are forced to merge, a phenomenon known as neutron drip occurs. Here, a crystalline lattice of exotic, super-heavy nuclei coexists with a superfluid ocean of free neutrons, protons, and electrons. The neutrons drip out of the nuclei, becoming part of the free-flowing superfluid, while the remaining nuclei become increasingly bizarre, containing hundreds of neutrons for every proton. This inner crust, extending perhaps a kilometer or two, is a transitional zone where matter begins its complete transformation into neutronium. The The true heart of the neutron star, its outer core, begins where the nuclei finally vanish altogether. This region, extending several kilometers inward, is primarily composed of a superfluid of neutrons. A superfluid is a state of matter that behaves like a fluid with zero viscosity, flowing without any friction. Imagine a liquid that can climb walls or spin endlessly without losing energy. That's a superfluid. Within this neutron superfluid, there are also smaller populations of degenerate protons and electrons forming a superconducting plasma. The protons and electrons are degenerate in the quantum sense, meaning they are packed so tightly that their momentum states are filled to the brim, generating immense pressure. The protons, being charged, also form a superconductor, a material that conducts electricity with perfect efficiency, without any resistance. This combination of superfluid neutrons and superconducting protons-electrons creates an environment of truly exotic quantum mechanics, where friction and electrical resistance are non-existent. But even more mysterious and speculative is the inner core, the very center of the neutron star. Here, at densities exceeding those of atomic nuclei by several times, and pressures so immense they are literally incalculable by current means, the nature of matter is unknown. Theoretical models propose a menagerie of exotic possibilities. Could the neutrons themselves break down into their constituent quarks, up and down quarks, forming a quark-gluon plasma, a state of matter thought to exist only for fleeting moments after the Big Bang? Or might new, heavier particles called hyperons emerge, particles containing strange quarks? Some theories even suggest the formation of strange quark matter, a hypothetical stable form of matter composed of an equal mixture of up, down, and strange quarks, potentially more stable than ordinary nuclear matter. This region remains the most profound frontier of neutron star research, a realm where the fundamental building blocks of the universe might be rearranged into entirely new forms. The extreme conditions make direct observation impossible, leaving us to rely on sophisticated theoretical physics and the subtle gravitational signatures these objects leave behind. The stability of this entire structure, from crust to core, is not due to chemical bonds or atomic forces, but to the sheer, unyielding power of neutron degeneracy pressure. This quantum mechanical phenomenon is a direct consequence of the Pauli exclusion principle applied to neutrons. Just as electrons resist being in the same quantum state, so too do neutrons. When gravity tries to compress them further, this quantum pressure pushes back with incredible force, preventing the star from collapsing into an even smaller, denser object, a black hole. It is a battle between the universe's most powerful force, gravity, and the fundamental rules of quantum mechanics. For neutron stars, quantum mechanics wins, holding the line against complete gravitational collapse, at least for now. This critical balance defines the very existence of a neutron star, keeping it from crossing the event horizon and becoming an invisible cosmic abyss. So, when we speak of a teaspoon of neutron star matter, we are referring to a fraction of a cubic centimeter of this neutron-degenerate exotic substance. It is a sample of matter stripped down to its most fundamental components, packed beyond comprehension, governed by quantum laws that defy our everyday intuition. It is the ultimate extreme of matter, a frozen moment of stellar collapse, teeming with the raw, unbridled forces of the atomic nucleus, yet held together by a quantum repulsion that is truly magnificent in its power. This isn't just a heavy rock, it's a cosmic titan miniaturized, a piece of a star where the laws of physics are stretched to their most profound and wondrous limits. The very concept challenges our imagination, preparing us for the truly destructive power contained within such a tiny, seemingly innocuous volume. Now, we arrive at the chilling thought experiment. What if, by some impossible feat of cosmic engineering, a single teaspoon of this unimaginable neutron star matter were to be brought to Earth? No, not just brought, but released onto our planet's surface. The consequences would be instantaneous, catastrophic, and utterly beyond anything our world has ever experienced. This isn't a slow burn, it's a quantum singularity unleashed, a localized gravitational apocalypse. First, consider the sheer mass. As established, a single teaspoon of neutron star material holds the mass of 3 billion tons. That is the equivalent of 600 Great Pyramids of Giza, or roughly 1/500 Empire State Buildings. To put it another way, it's the weight of over 2,000 fully loaded aircraft carriers, condensed into a volume smaller than a child's toy. When this infinitesimally small object, yet possessing such gargantuan mass, encounters Earth, its gravitational pull would be immediate and overwhelmingly dominant in its immediate vicinity. The initial impact would be less of an explosion and more of an instantaneous localized collapse. There would be no mushroom cloud, no spreading firestorm in the conventional sense. Instead, the teaspoon of neutron star matter would punch through whatever surface it landed on as if it were made of tissue paper. Imagine dropping a lead bullet into a vat of thick syrup. That bullet would still sink. Now, replace the syrup with the densest rock on Earth, and the bullet with something millions of times denser than anything known. The neutronium would not merely sink, it would accelerate, driven by its own immense self-gravity and the Earth's comparatively puny gravitational attraction. As it plunges through the Earth's crust, the neutron star matter would not interact chemically with terrestrial elements in the way we understand. Its constituent neutrons are already packed beyond the forces of electromagnetism or chemical bonds. The matter it encounters would be pulverized, vaporized, and then simply pushed aside. The resistance it would face from solid rock, liquid magma, or even Earth's iron core would be negligible. Think of a hot knife slicing through butter, but on a scale so grand that the knife is a tiny, super-dense object, and the butter is the entire planet. The neutronium would create a perfect cylindrical bore straight down through the planet, like a cosmic drill bit of unimaginable power. The path of this miniature star fragment would be defined by its descent towards the Earth's gravitational center. It would accelerate, not decelerate. The incredible pressure exerted by the neutronium would compress the surrounding material to a fraction of its volume, generating immense heat and pressure. This isn't just a simple displacement of matter. It's a shockwave of density, forcing Earth's material to yield in ways it has never evolved to handle. The surrounding rock and metal would momentarily behave as if it were a superheated plasma, then be shunted aside as the neutronium continues its plunge. The extreme gravitational gradient around this tiny speck of neutron star matter would generate unimaginable tidal forces. Anything in its immediate vicinity would be stretched and torn apart. Imagine the force of a black hole's event horizon, but concentrated on a microscopic scale. If you were standing even hundreds of meters away, your body would be subjected to differential gravitational pulls so extreme that your feet would be pulled downwards with exponentially more force than your head. Your atomic bonds, the very integrity of your molecular structure, would fail instantly, tearing you apart into a stream of subatomic particles. This isn't just a crushing force, it's a rending, twisting force that unravels matter from within. The descent would continue, rapidly accelerating. Within seconds, the teaspoon of neutronium would reach the Earth's core. Here, it would briefly oscillate. Having built up tremendous momentum, it would overshoot the exact center, slightly slowing as it passed through the most massive part of the core, then accelerating again as it approached the opposite side of the planet. It would be a pendulum of pure gravity, swinging through the Earth's interior, each pass vaporizing more material and expanding its subterranean tunnel. Each oscillation would create immense seismic disturbances, a series of global earthquakes that would dwarf anything in Earth's geological history. The entire planet would shudder, groan, and eventually begin to fracture. As the neutronium oscillates, it would be shedding energy, not through friction, but through gravitational interactions with the Earth's core. Each pass would convert some of its kinetic energy into heat within the Earth, further destabilizing the planet. The core, already a superheated liquid, would become a cauldron of unprecedented thermal and pressure chaos. The intense energy transfer would cause volcanic eruptions on a global scale, fissures ripping open continents, and oceans boiling away into superheated steam. The very surface of our planet would become a landscape of fire and ash, an uninhabitable wasteland. But the real, long-term horror lies in the interaction between the neutronium and ordinary matter. While the neutronium itself is stable under its own immense gravity, what happens if its surface is exposed to terrestrial material? The question is not fully settled, but theoretical physics suggests several terrifying possibilities. One theory postulates that if ordinary matter comes into contact with neutronium, it could be catalyzed into converting into neutron star matter itself. This isn't a chemical reaction, it's a nuclear transformation. If this strangelet theory holds true, the neutronium would not just pass through Earth, it would slowly, inexorably, begin to consume it. This process would start at the surface of the neutronium as it oscillates through the Earth. As it passes through the planet's core, a thin layer of Earth's iron and nickel would come into contact with the neutronium. This terrestrial matter, under the intense gravitational and nuclear forces, could be compressed and converted into neutronium. This would effectively make the teaspoon grow, ever so slightly with each pass. It would be a runaway reaction, a slow-motion consumption of our entire planet. The Earth would be transformed from the inside out, gradually becoming a sphere of neutron star matter, still incredibly dense, but a barren, dead relic of its former self. The ultimate fate of Earth, in this horrific scenario, would be its complete transformation. Over an extended period, perhaps days or weeks, depending on the exact physics of the conversion, our vibrant living planet would be cannibalized by this tiny, impossibly dense invader. The Earth would shrink, its diameter diminishing as its mass became ever more concentrated. The very ground beneath our feet would cease to exist in its familiar form, instead becoming a super-dense, neutron-degenerate sphere. All life, all oceans, all mountains, all history would be erased, compressed out of existence into a silent, featureless ball of nuclear matter. It is a vision of absolute destruction, not from an external impact, but from an internal, self-consuming force of gravity. A single teaspoon, the size of a child's marble, becoming the undoing of an entire world. This is the true power and terror of neutron star matter. The implications are not just destructive, they are transformative, fundamentally altering the very state of our planet. The scenario of a neutron star fragment encountering Earth is less an impact and more an instantaneous gravitational dissection. As the minute speck of neutronium, carrying the mass of billions of tons, touches the Earth's surface, the planet's resistance would be a desperate, futile struggle against an insurmountable force. The immediate aftermath would not be a crater, but a perfect superheated tunnel carved straight through our world, a testament to the neutronium's relentless downward acceleration. Imagine the strongest diamond, the most unyielding tungsten, pitted against this cosmic intruder. Even at the atomic level, the structures that give these materials their strength are built on electromagnetic bonds, the forces holding electrons to nuclei and atoms to each other. But neutronium's density bypasses these forces entirely. It's a collection of neutrons packed so tightly that the strong nuclear force itself is the dominant interaction, a realm where electromagnetic repulsion is trivial. So, as the neutronium plunges into Earth's crust, the atomic structures of terrestrial matter simply collapse. The nuclei of iron, silicon, and oxygen are momentarily subjected to pressures so extreme they are effectively vaporized, their constituent protons and electrons forced into each other, converting them into a state closer to neutron-degenerate matter. This isn't chemical dissolution, it's nuclear unmaking, a state where Earth's very elements lose their identity. The passage of the neutronium would be accompanied by an intense, localized flash of energy, not from a chemical explosion, but from the immense kinetic energy of the falling object and the shock waves generated by its passage. The surrounding rock would be heated to temperatures that rival the surface of the Sun, instantly turning solid granite into a superheated plasma, then into a vacuum as the neutronium passes. The channel carved by the falling teaspoon would be a temporary void, constantly being created and consumed as the object plummets. Its speed would rapidly approach escape velocity through the Earth, accelerating to tens of thousands of kilometers per second. To visualize this, consider a bullet fired from a rifle, moving at perhaps a kilometer per second. Now imagine an object 3 billion times heavier, accelerating through solid rock at 30 times that speed. The sheer scale shift is incomprehensible. As it drills deeper, through the mantle and towards the outer core, the ambient pressure from Earth's own immense gravity increases dramatically. At these depths, matter is already under crushing pressure and high temperatures, but it's still fundamentally atomic. The neutronium, however, would still treat this superheated semi-liquid rock as if it were air. The incredible differential in density would mean the Earth's internal structure offers almost no resistance to its passage. The path it creates would be a transient tunnel of superheated plasma collapsing in on itself as the neutronium sweeps past. The pressure wave ahead of the neutronium would be immense, a localized supercompression event that would briefly mimic conditions inside a nuclear fusion reactor, but without the corresponding fusion. Upon reaching the Earth's core, a region of liquid iron and nickel under pressures of millions of atmospheres and temperatures hotter than the Sun's surface, the neutronium would not stop. It would continue its trajectory, driven by inertia and the Earth's gravitational pull. Its deceleration as it passed through the core would be minimal. It would overshoot the exact center of the Earth and continue towards the opposite side, the sheer momentum of its billions of tons of mass carrying it through. This passage would create a gravitational and seismic nightmare for the planet. Each time the neutronium passed through the core, it would generate colossal tremors, not just local earthquakes, but planet-spanning seismic events. The Earth would vibrate like a gong struck by a cosmic hammer, its entire geological structure stressed to breaking point. These oscillations, the neutronium pendulum swinging back and forth through the Earth's interior, would have devastating effects on the planet's stability. With each pass, the neutronium would interact gravitationally with the Earth's core, transferring minute amounts of energy, but creating immense tidal stresses. The Earth's rotation and its magnetic field, generated by the convection of its liquid outer core, would be violently perturbed. The molten iron, already in a state of turbulent motion, would be subjected to unprecedented gravitational stresses, potentially disrupting the geodynamo that protects Earth from solar radiation. This disruption could lead to a rapid weakening or even collapse of the magnetic field, leaving our atmosphere vulnerable to the solar wind and cosmic rays, effectively sterilizing the surface. Furthermore, the persistent passage of such a dense object would create a tunnel of superheated deatomized matter. Although this tunnel would attempt to collapse and refill, the constant oscillation would prevent a stable seal. The resulting instability would manifest as global volcanism on an unprecedented scale. Gigantic volcanic eruptions would rip open the planet's crust, spewing magma and ash into the atmosphere, leading to a rapid and catastrophic climate shift. The oceans would boil, the atmosphere would be choked with sulfur and dust, and the surface would become utterly uninhabitable within hours. The planet would be literally boiling from the inside out, its internal heat escaping through massive fissures. The most terrifying long-term consequence, as alluded to previously, involves the theoretical possibility of phase transition. While the neutronium is stable due to neutron degeneracy pressure, contact with normal baryonic matter, especially under the extreme pressures and temperatures of Earth's core, might trigger a catalytic conversion. This is the Strangelet hypothesis, where ordinary matter, upon contact with strange quark matter, a theoretical form of ultra-dense matter thought to exist in the inner cores of some neutron stars, converts into strange quark matter itself. If our hypothetical teaspoon were composed of such strange matter, or if the conditions allowed for the conversion of normal matter into neutronium, the Earth's struggle would be tragically brief. With each oscillation through the Earth's core, a thin layer of surrounding terrestrial matter would be infected and converted. This would not be a rapid, explosive transformation, but a slow, relentless erosion from within. The teaspoon of neutronium would gradually grow, millimeter by millimeter, accumulating the mass of our planet, until the entire Earth was transformed into a larger, perfectly spherical, utterly inert lump of neutron star material. Our blue planet, once teeming with life, would become a silent, super-dense sphere, a stellar relic in miniature. The Earth would shrink dramatically, its diameter potentially reduced to just a few hundred meters, while retaining its original mass. The very concept of Earth would cease to exist, replaced by a quantum-locked husk. This is the ultimate desperate resistance of Earth. A valiant but ultimately futile stand against a force of cosmic density that simply cannot be overcome by the familiar laws governing our world. The planet would fight, it would shudder and break, but ultimately it would yield, utterly consumed by a single, impossible speck of matter. Having glimpsed the terrifying potential of a neutron star fragment on Earth, let us now journey back to its true cosmic home, the neutron star itself. These stellar remnants are not merely uniform balls of dense matter, they possess a complex, layered internal structure, a miniature universe of exotic physics, where the laws we understand on Earth are twisted and transformed by unimaginable pressures and densities. Peering into their unseen depths is like deciphering a cosmic riddle, revealing states of matter that challenge the very foundations of our knowledge. The neutron star's interior is generally categorized into distinct layers: an outer crust, an inner crust, an outer core, and a mysterious inner core. Each layer represents a unique phase of matter, a consequence of the ever-increasing pressure as one descends towards the star's heart. Understanding these layers is key to comprehending the bizarre stability of these objects and how they resist complete gravitational collapse. The outermost layer, the outer crust, is a mere few hundred meters thick, yet its density is already mind-boggling, millions of times denser than anything found on Earth. Here, the atoms are not merely compressed, they are fundamentally altered. Electrons are still present, but they are no longer bound to individual nuclei in neat orbits. Instead, they form a relativistic electron gas, a sea of particles moving at speeds approaching that of light. The atomic nuclei, meanwhile, are super heavy and incredibly neutron-rich, far beyond anything stable on Earth. Imagine nuclei with hundreds of neutrons for every proton, packed into a rigid crystalline lattice. This lattice gives the neutron star its incredibly smooth, almost perfectly spherical. This crystalline structure, despite the extreme conditions, is somewhat analogous to a superdense metal, yet its properties are governed by quantum mechanics rather than classical chemistry. Delving deeper, we encounter the inner crust, a transitional zone spanning a kilometer or two. Here, the pressure intensifies to the point where atomic nuclei begin to lose their individual identities. This is where the phenomenon of neutron drip occurs. The gravitational squeeze becomes so powerful that neutrons are forced out of the nuclei, forming a vast superfluid ocean of free neutrons that coexists with a lattice of increasingly exotic, super-heavy nuclei. These nuclei are so neutron-rich they are often referred to as nuclear pasta due to their hypothesized shapes. Under extreme pressure, the strong nuclear force starts to sculpt nuclei into complex geometries, like spaghetti, lasagna, or even Swiss cheese, before they completely dissolve. The superfluid neutrons flow without any viscosity, a quantum fluid defying friction. This inner crust is a bizarre blend of solid-like nuclei and frictionless liquid neutrons, a state of matter utterly alien to our everyday experience. Beyond the inner crust lies the outer core, the dominant volume of the neutron star, extending for several kilometers towards the center. This region is a true sea of neutronium, primarily composed of a degenerate superfluid of neutrons. The term degenerate here refers to a quantum mechanical state where particles completely filled, preventing further compression due to the Pauli exclusion principle. This pressure is the primary force resisting gravity. Interspersed within this neutron superfluid are smaller populations of degenerate protons and electrons. These charged particles, under such extreme conditions, form a superconducting fluid. This means they conduct electricity with zero resistance, creating an incredibly powerful, persistent magnetic field that can be trillions of times stronger than Earth's, that makes the outer core a truly unique quantum mechanical environment, a cosmic laboratory where fundamental forces play out on a macroscopic scale. The most enigmatic and theoretically rich region is the inner core, the very heart of the neutron star, where densities can exceed 5 to 10 times that of an atomic nucleus. Here, our understanding of matter breaks down and theoretical models diverge dramatically. The pressure is so immense that even the neutron degeneracy pressure might be overcome, leading to a phase transition where neutrons themselves might dissolve into their constituent quarks, up, down, and potentially strange quarks. This could result in the formation of quark matter, or that is believed to have existed only for a fleeting moment after the Big Bang, just before the universe cooled enough for quarks to bind into protons and neutrons. If quark matter exists here, it would be composed of free-moving quarks, no longer confined within individual particles. Another theoretical possibility for the inner core is the existence of hyperons. These are heavier baryons, particles similar to protons and neutrons, but containing one or more strange quarks. As density increases, it becomes energetically favourable for neutrons to convert into hyperons, introducing new exotic particles into the dense mix. The exact composition of the inner core remains one of the most significant unsolved mysteries in astrophysics. Scientists rely on sophisticated numerical simulations and indirect observations, like precise measurements of neutron star masses and radii, to try and constrain these theoretical models. The equation of state for this ultra-dense matter, which describes how pressure relates to density, is a critical puzzle piece for understanding the internal structure and evolution of these stars. The immense gravitational field of a neutron star means that its surface gravity is hundreds of billions of times stronger than Earth's. If you were to drop an object from just 1 meter above a neutron star's surface, it would hit the surface at speeds exceeding 2,000 kilometers per second in less than a microsecond. This profound gravity also severely warps spacetime around the star, causing phenomena like gravitational lensing where the star's own light can be bent around it, allowing us to see parts of its far side. These extreme conditions also make neutron stars cosmic laboratories for testing the fundamental laws of physics. They are unique environments where quantum mechanics, general relativity, and nuclear physics all intersect. By studying their properties, their masses, radii, spin rates, and cooling behavior, scientists hope to unlock the secrets of matter at its absolute limit, providing insights into the strong nuclear force, the nature of dark matter, and even the existence of exotic particles. The continued study of these unseen depths promises to revolutionize our understanding of matter itself, revealing whether the universe holds even stranger states of existence hidden within these collapsed stellar hearts. The ongoing quest to map these interiors is a testament to human ingenuity, using distant echoes and subtle gravitational interactions to paint a picture of the most alien landscapes in the cosmos. Our understanding of the exotic, unseen depths of neutron stars isn't derived from direct observation, but from a profound cosmic phenomenon they exhibit: their ability to act as precise celestial lighthouses. These are pulsars, rapidly spinning neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep across space, and if one happens to intersect with Earth, we observe a rhythmic pulse, like a cosmic lighthouse signaling across the vast interstellar void. It is through these rhythmic pulses that we detect and characterize these otherwise invisible giants. The discovery of pulsars in 1967 by Jocelyn Bell Burnell and Anthony Hewish was initially met with bewilderment, even humorously attributed to little green men, due to their precise periodicity. But further research quickly revealed their true nature: the rapidly rotating, highly magnetized remnants of supernovae. A pulsar's rotation rate can be astonishing, ranging from a few times per second to hundreds of times per second for millisecond pulsars. Imagine an object the size of a city spinning as fast as a kitchen blender. This incredible rotational speed is a relic of the original star's collapse. As the massive star shrinks, its angular momentum is conserved, causing it to spin up dramatically, much like a figure skater pulling in their arms. The magnetic fields of pulsars are equally extreme, billions to trillions of times stronger than Earth's magnetic field. These colossal magnetic fields are thought to be generated by the superconducting proton-electron fluid in their outer cores, amplified during the stellar collapse. The magnetic axis of a pulsar is often misaligned with its rotational axis, creating the lighthouse effect. Charged particles, primarily electrons, are accelerated along these powerful magnetic field lines, emitting synchrotron radiation, a focused beam of radio waves, X-rays, or even gamma rays. It is this beam, sweeping across our telescopes, that allows us to detect them and provides a wealth of information about their properties. The regularity of pulsar pulses is astounding. Some pulsars are more accurate timekeepers than even the best atomic clocks on Earth, gradually slowing down over millions of years as they radiate away energy. This incredible precision makes them invaluable astrophysical tools, allowing scientists to conduct groundbreaking experiments. For instance, by timing pulses in binary systems, scientists can precisely measure the orbital decay caused by the emission of gravitational waves, a direct confirmation of Einstein's general theory of relativity decades before direct detection by LIGO. The Hulse-Taylor binary pulsar, discovered in 1974, provided the first observational evidence for gravitational waves, earning a Nobel Prize. Furthermore, these cosmic lighthouses serve as probes for the interstellar medium. As pulsar signals travel through the vast stretches of space between the pulsar and Earth, they encounter clouds of ionized gas. The electrons in this plasma cause the radio waves to disperse, meaning different frequencies arrive at slightly different times. By measuring this dispersion measure, astronomers can determine the amount of free electrons along the line of sight, effectively mapping the electron density of our galaxy. This technique has allowed us to chart the invisible gas clouds that permeate our galaxy, revealing its intricate structure. The timing of pulsar signals can also be used to search for gravitational waves, not just from merging neutron stars, but from the fabric of spacetime itself. The Pulsar Timing Array (PTA) experiments, such as nanograv, use an array of precisely timed pulsars scattered across the galaxy. Gravitational waves passing through our region of space would subtly stretch and compress spacetime, causing tiny, measurable variations in the arrival times of these pulsar pulses. By looking for correlated patterns in the timing residuals from many pulsars, scientists hope to detect a gravitational wave background, a faint hum of gravitational waves from all the supermassive black holes merging throughout the universe. This would be a groundbreaking discovery, opening a new window into the low-frequency gravitational wave universe. Even more intriguing is the use of pulsars to probe the extreme conditions within neutron stars. The rate at which a pulsar spins and how it gradually slows down provides clues about its internal structure and the nature of neutronium. For instance, glitches occur when a pulsar suddenly speeds up by a tiny but measurable amount. These glitches are thought to be caused by sudden transfers of angular momentum from the star's superfluid interior to its solid crust. By studying the frequency and magnitude of these glitches, scientists can infer properties of the superfluid neutron component in the inner crust and outer core, providing a unique insight into a state of matter impossible to recreate in a terrestrial laboratory. The intense magnetic fields also play a critical role in the evolution of neutron stars. In some cases, the magnetic field can be so powerful that it causes a magnetar to form. Magnetars are a rare type of neutron star with magnetic fields 1,000 times stronger than typical pulsars, up to a quadrillion times stronger than Earth's. These extreme fields can undergo starquakes in the neutron star's crust, releasing enormous bursts of gamma rays and X-rays, known as soft gamma repeaters or anomalous X-ray pulsars. These events are among the most energetic in the universe, demonstrating the profound influence of magnetic forces in these superdense objects. Beyond their practical uses, pulsars are cosmic beacons reminding us of the violent beauty of stellar evolution. Each pulse reaching Earth is a whisper from a star that died billions of years ago, a message carried across unimaginable distances. They are tangible evidence of general relativity and quantum mechanics working in concert under the most extreme conditions. The existence and properties of these celestial lighthouses are not just fascinating scientific curiosities. They are foundational to our understanding of superdense matter, providing the only direct observational window into the exotic interiors of neutron stars and the fundamental forces that govern them. Without their steady, precise rhythm, much of the universe's most extreme physics would remain forever shrouded in mystery, making them truly indispensable tools in the cosmic documentarian's arsenal. While individual neutron stars offer a glimpse into the extremes of matter, their most spectacular and cosmically significant events occur when two of these ultra-dense relics collide. These cataclysmic mergers give rise to phenomena known as kilonovae, explosions that are far more powerful than a standard supernova, yet less luminous than the hypernovae associated with black hole formation. Kilonovae are not just brilliant celestial fireworks, they are the universe's primary factories for forging the heaviest elements, including the gold in your jewellery and the platinum in your electronics. Without these titanic collisions, much of the periodic table would simply not exist. The story of a kilonova begins with a binary system. Two neutron stars, born from separate supernova events, locked in an intricate gravitational dance. Over billions of years, these cosmic waltzes slowly spiral inward, losing orbital energy by emitting gravitational waves, ripples in the fabric of spacetime itself. This process, predicted by Einstein's general relativity, causes their orbits to shrink, bringing them ever closer, accelerating their deadly ballet. The final moments of this celestial dance are incredibly swift. The neutron stars drawing closer and closer, spinning faster and faster around each other until their surfaces are mere kilometers apart. The climax arrives when the two neutron stars finally touch. The collision is not a gentle embrace, but a violent, instantaneous smash-up of unimaginable force. The neutron stars, being rigid beyond comprehension, literally tear each other apart. Their ultra-dense matter, already at the limit of compression, cannot withstand the impact. A fraction of their material is violently ejected into space at relativistic speeds, forming a superheated, rapidly expanding cloud of neutron-rich debris. This ejected material, now released from the extreme gravitational confines of the neutron star, begins to decompress and cool, triggering a cascade of exotic nuclear reactions. This is where the magic of nucleosynthesis, the creation of new elements, truly shines. The ejected material is extraordinarily rich in free neutrons. Under normal stellar conditions, heavy elements are built up through a process called the S process, slow neutron capture, in red giant stars, which slowly adds neutrons to atomic nuclei. But in the neutron-rich environment of a kilonova, a different process dominates, the R process, rapid neutron capture. Here, atomic nuclei are bombarded by an overwhelming flux of free neutrons, capturing them far faster than they can undergo radioactive decay. This rapid neutron capture builds up incredibly heavy, unstable nuclei. Once the neutron flux subsides, these unstable nuclei rapidly decay through a series of beta decays, transforming neutrons into protons, and thereby creating a dazzling array of the heaviest stable elements in the universe. This R process is the only known astrophysical mechanism capable of producing elements heavier than iron, such as gold, platinum, uranium, and thorium in the observed cosmic abundances. For decades, scientists hypothesized about the origins of these elements, with some theories pointing to very massive supernovae. However, kilonovae have emerged as the leading candidates, capable of explaining the observed cosmic inventory of these precious heavy metals, the gold in your ring, the uranium powering nuclear reactors, the rare earth elements essential for modern technology. All were very likely forged in the heart of a kilonova, billions of years ago in a galaxy far away. The first direct observation of a kilonova, designated GW170817, was a monumental scientific breakthrough. In August 2017, the LIGO and Virgo gravitational wave observatories detected gravitational waves emanating from the merger of two neutron stars. This event, lasting for about 100 seconds, was followed almost immediately by a burst of gamma rays detected by space telescopes. Within hours, optical telescopes pinpointed the exact location of the explosion in a galaxy called NGC 4993, just 130 million light-years away. For the first time, scientists had observed a cosmic event in both gravitational waves and electromagnetic radiation, a triumph of multi-messenger astronomy. The subsequent electromagnetic observations of GW170817 provided irrefutable evidence for the kilonova phenomenon. Spectroscopic analysis of the expanding debris cloud revealed the unmistakable signatures of newly synthesized heavy elements, confirming that the R process had indeed occurred. The light curve of the kilonova, its brightness evolving over time, matched theoretical predictions for an event powered by the radioactive decay of these newly formed, unstable heavy nuclei. It was a spectacular confirmation of decades of theoretical work. A moment when abstract physics became tangible cosmic reality. The study of kilonovae continues to refine our understanding of nuclear physics under extreme conditions. By analysing the light and gravitational wave signals from these events, scientists can probe the equation of state of neutron star matter, how pressure and density relate within these objects. This is crucial for understanding the composition of the inner core, potentially revealing the existence of quark matter or hyperons. The precise timing and intensity of the gravitational wave signal also provide constraints on the masses of the merging neutron stars and their spins, offering insights into their formation and evolution. The legacy of kilonovae extends far beyond their immediate cataclysmic brilliance. They are the cosmic alchemists, enriching the universe with the very elements necessary for complex chemistry, planetary formation, and ultimately, life itself. Without these violent mergers, our planet would be a very different place, devoid of many of the materials we consider essential. Every atom of gold, every speck of platinum is a direct echo of a kilonova event, a reminder that the most precious substances are born from the most extreme cosmic violence. These events demonstrate how the seemingly abstract world of ultra-dense matter and quantum forces directly shapes the material reality of our everyday lives, connecting the subatomic realm to the grandest cosmic spectacles. They are truly the universe's ultimate foundries, forging existence from stellar death. Neutron stars represent a precarious balance, a quantum mechanical bulwark against the universe's ultimate gravitational predator, the black hole. They are objects hovering on the very brink of complete gravitational collapse, held together by the immense pressure of neutron degeneracy. But this defense has its limits. Push a neutron star too far, add just a little too much mass, and even the unyielding force of neutron degeneracy pressure will fail, leading to an irreversible descent into the cosmic abyss. This transition, from the densest matter to the ultimate cosmic vacuum, marks the boundary where the known laws of physics effectively cease to apply. The critical threshold for a neutron star, beyond which it can no longer support itself, is known as the Tolman-Oppenheimer-Volkoff, or TOV, limit. While the exact value is still a subject of active research due to uncertainties in the equation of state of superdense matter, it is estimated to be around 2 to 2.5 times the mass of our Sun. This means a neutron star can support a mass roughly double that of the Chandrasekhar limit for white dwarfs, but not indefinitely. Should a neutron star accumulate mass beyond this point, perhaps through accretion from a companion star, or by merging with another neutron star, its fate is sealed. Consider a neutron star in a binary system, orbiting a larger, less evolved companion star. If the companion is close enough, the neutron star's ferocious gravity can begin to strip away its outer layers, siphoning off stellar material. This process, known as accretion, gradually adds mass to the neutron star. As the mass increases, the star's core compresses further, and the neutron degeneracy pressure is pushed to its absolute maximum. It's a cosmic tightrope walk. For a time, the star can maintain its equilibrium, but there's a point of no return. Once the TOV limit is breached, the collapse is catastrophic and instantaneous. There is no gentle settling, no gradual shrinking. The star implodes with a speed approaching the speed of light, its constituent neutrons losing their battle against gravity. In a fraction of a second, the entire object collapses inward, compressing endlessly to an infinitely small point in spacetime, a singularity. At this moment, an event horizon forms around the singularity, a boundary from which nothing, not even light, can escape. The neutron star vanishes, becoming a black hole, a region of spacetime so warped that it is cut off from the rest of the universe. This transition from neutron star to black hole is a profound event, marking the ultimate triumph of gravity. It is a moment when the strongest known force in the universe, the strong nuclear force, and the quantum mechanical resistance of neutron degeneracy are finally overcome. The exotic matter that once comprised the neutron star is compressed beyond recognition, its properties lost behind the veil of the event horizon. What exactly happens to the neutronium at the singularity remains one of the deepest mysteries of physics, a realm where general relativity predicts infinite density and quantum mechanics struggles to offer a coherent description. The search for a theory of quantum gravity is, in part, an attempt to understand what truly lies at the heart of a black hole. The merger of two neutron stars, as observed in GBU 170817, offers a direct pathway to black hole formation. After the initial kilonova explosion, the remaining dense core, formed from the fused remnants of the two neutron stars, can briefly exist as a hypermassive neutron star. This object is spinning incredibly fast, and is likely supported by a combination of neutron degeneracy pressure and its rapid rotation. However, this state is transient. As the hypermassive neutron star sheds angular momentum through gravitational wave emission and other processes, its internal pressure can no longer support its immense mass. It collapses within milliseconds, forming a new black hole. The gravitational wave signal from such a merger provides a unique signature of this final collapse, a sudden cut-off of the high-frequency gravitational waves as the event horizon forms. The formation of black holes from neutron stars is a fundamental process in astrophysics, shaping the evolution of galaxies and the distribution of matter in the cosmos. These stellar mass black holes, typically 3 to 20 times the mass of our Sun, are common remnants of massive stellar evolution. They are distinct from the supermassive black holes found at the centres of galaxies, which form through different, less understood processes, likely involving the accretion of vast amounts of gas and mergers of smaller black holes. Understanding the neutron star to black hole transition is crucial for accurately predicting the population of black holes in our universe and for interpreting the gravitational wave signals detected by observatories like LIGO and Virgo. Moreover, this boundary pushes the limits of our theoretical understanding, which determines how much pressure a given density of matter can exert, is directly constrained by the TOV limit. If we can precisely measure the maximum mass of an observed neutron star, it tells us about the stiffness of neutronium. A stiffer equation of state allows for more massive neutron stars before collapse, suggesting that the matter inside them is even more resistant to compression. Conversely, a softer equation of state implies a lower TOV limit, potentially favouring the existence of exotic matter like quark gluon plasma in their cores. The study of this ultimate transition also sheds light on the nature of space and time itself. The formation of an event horizon is a dramatic illustration of general relativity in action, where gravity becomes so extreme that it dictates the very geometry of spacetime, trapping everything within its grasp. It is a boundary beyond which cause and effect can no longer propagate outwards, a one-way membrane into oblivion. For all their incredible density and exotic matter, neutron stars are still objects we can, in principle, understand and describe. Black holes, however, represent a deeper mystery, a region where our current physics breaks down and a new, unified theory of quantum gravity is desperately needed. The journey from a fiery stellar core through the incredible compression of neutronium to the silent, invisible embrace of a black hole is the ultimate narrative of matter's struggle against gravity, a struggle that sometimes, inevitably, ends in defeat. It is a stark reminder that even the densest matter in the universe has its breaking point, beyond which lies a realm of absolute nothingness that is nonetheless the most gravitationally powerful entity in the cosmos. Neutron stars are not merely cosmic curiosities or harbingers of destruction. They are unparalleled natural laboratories, offering scientists a unique opportunity to probe the fundamental laws of physics under conditions utterly unattainable on Earth. Here, general relativity, quantum mechanics, and nuclear physics converge, creating an environment where theories can be tested and new insights into the universe's most extreme phenomena can be gleaned. The sheer scale of their density and gravity transforms them into cosmic magnifying glasses for the most profound scientific questions. One of the foremost puzzles neutron stars help us address is the equation of state, EOS, of ultra-dense matter. This equation describes how matter behaves under extreme pressure, how much pressure it exerts for a given density. On Earth, we understand the EOS for gases, liquids, and solids relatively well. But at the densities found within a neutron star, which can reach hundreds of millions of tons per cubic centimetre, the EOS becomes incredibly complex and poorly understood. It dictates the star's radius for a given mass, the maximum mass it can support before collapsing into a black hole, the TOV limit, and the composition of its enigmatic core. By precisely measuring the masses and radii of neutron stars, astronomers can constrain the EOS, distinguishing between competing theoretical models that predict different internal compositions, such as pure neutronium, quark matter, or hyperons. For instance, if observations consistently show neutron stars with large radii for their mass, it suggests a stiffer EOS, where matter is more resistant to compression. This might rule out theories that predict easily compressible quark matter in the core. Conversely, smaller radii for a given mass would point towards a softer EOS, possibly indicating the presence of exotic, more compressible phases of matter. Projects like the Neutron Star Interior Composition Explorer (NICER) on the International Space Station are specifically designed to measure neutron star radii with unprecedented accuracy by observing X-ray emission from their surfaces. These precise measurements are crucial for peeling back the layers of these celestial objects and revealing what truly lies within. Neutron stars also serve as a unique testing ground for Einstein's theory of general relativity. As described earlier, binary pulsars, systems of two neutron stars orbiting each other, provide exquisite validation of general relativity's predictions, particularly regarding the emission of gravitational waves. The orbital decay of these systems, measured with incredible precision, perfectly matches Einstein's predictions. Beyond this, the extreme gravitational fields of isolated neutron stars can be used to test subtle effects of general relativity, such as the Shapiro delay, where light passing near a massive object takes longer to reach an observer. Future observations with next-generation telescopes could even detect frame-dragging effects, where a rapidly spinning neutron star literally twists spacetime around it, a prediction of general relativity that is extremely difficult to observe elsewhere. The powerful magnetic fields of neutron stars, especially magnetars, offer another window into extreme physics. These fields are orders of magnitude stronger than any magnetic field we can create in a lab, studying their origin, evolution, and interactions with the neutron star crust provides insights into magnetohydrodynamics, the study of electrically conducting fluids in magnetic fields under conditions that strain our current theoretical models. Phenomena like magnetoflares, sudden bursts of X-rays and gamma rays, are thought to be caused by starquakes in the neutron star's crust, releasing immense magnetic energy. These events are not just spectacular, they provide data on the strength and shear resistance of the neutron star crust, which is itself a unique state of matter. Furthermore, neutron stars are crucial for understanding the behavior of matter at ultra-low temperatures and extremely high densities, leading to phenomena like superfluidity and superconductivity on a cosmic scale. The free neutrons in the inner crust and outer core of a neutron star are believed to exist in a superfluid state, flowing without friction. Similarly, the protons in the outer core are thought to be superconducting, conducting electricity with zero resistance. The existence of these quantum states in such a massive celestial object is a profound demonstration of quantum mechanics at work. Observing glitches in pulsar spin rates, where a neutron star suddenly speeds up, provides indirect evidence for these superfluid interiors. These glitches are attributed to sudden transfers of angular momentum from the frictionless superfluid interior to the solid outer crust. By studying these events, scientists can probe the properties of these quantum fluids, which could never be studied in a laboratory environment. Neutron stars also play a vital role in our understanding of nucleosynthesis and the origin of elements. As we learned from kilonovae, the merger of two neutron stars is the primary site for the rapid neutron capture process, or R process, responsible for creating heavy elements like gold, platinum, and uranium. Without neutron stars and their mergers, the universe would be a much poorer place in terms of elemental diversity. Studying the debris from kilonovae provides direct evidence of these processes, allowing scientists to refine models of how elements are forged in the cosmos and how they are distributed throughout galaxies. Finally, neutron stars could potentially host exotic particles or dark matter interactions. If dark matter particles interact even weakly with ordinary matter, they might accumulate within the dense core of a neutron star, potentially altering its properties or leading to observable signals. Some theories propose that neutron stars could even be dark stars if they accrue enough dark matter, leading to internal heating or collapse. While highly speculative, these possibilities highlight how neutron stars, by virtue of their extreme density and gravitational wells, become unique cosmic detectors for new physics beyond the standard model of particle physics. They are not just dead stars. They are living testaments to the universe's most extreme physics, continually challenging and expanding our understanding of reality. Each pulse, each merger, each subtle observation brings us closer to unraveling the deepest secrets of matter, gravity, and the very fabric of spacetime. From the terrifying thought experiment of a teaspoon of neutron star matter on Earth, to the cosmic lighthouses of pulsars and the elemental furnaces of kilonovae, our journey has traversed the most extreme frontiers of density and gravity. Yet, the story of neutron stars is far from complete. They are echoing monuments to the universe's most violent processes, carrying within them secrets that resonate with the very origins of matter and the fundamental laws that govern our cosmos. These echoes are not mere scientific data. They are profound insights into the nature of existence itself. The existence of neutron stars born from the spectacular demise of massive stars is a stark reminder of the recycling nature of the universe. The very elements that form our bodies, our planet, and indeed all the visible structures around us, were not present in the early universe. They were forged in the hearts of stars and scattered across space by supernovae, the same events that leave neutron stars in their wake. The carbon in our cells, the oxygen we breathe, the iron in our blood, all are products of stellar nucleosynthesis. But the heavier elements, the gold and platinum that symbolize wealth and rarity on Earth, carry a more dramatic lineage. They are the direct remnants of kilonovae, the mergers of neutron stars. Every atom of these precious metals is an echo of a cataclysmic collision, a cosmic whisper of extreme density and the rapid neutron capture process. Neutron stars are also cosmic time capsules, preserving conditions that have long vanished from the mainstream universe. The state of matter within them, where atomic structure is obliterated and neutrons are packed shoulder to shoulder, offers a glimpse into the early universe, albeit under different circumstances. The quark gluon plasma hypothesized to exist in their inner cores is akin to the matter that filled the universe a mere microsecond after the Big Bang. By studying neutron stars, we are in a sense reaching back in time, examining the universe's most primitive and fundamental building blocks under conditions of immense stress. They are living fossils of extreme physics, providing an active link to the quantum past. Moreover, these objects are the universe's most precise natural clocks and gravitational wave detectors. The rhythmic pulses of pulsars, some maintaining accuracy better than atomic clocks, have allowed us to confirm Einstein's century-old predictions about gravitational waves and to probe the invisible interstellar medium. The slight deviations in their timing, the mysterious glitches, offer an unparalleled window into the superfluid and superconducting properties of matter within their cores, quantum phenomena playing out on a macroscopic scale. These aren't just theoretical constructs, they are observable, measurable realities, demonstrating the power of indirect astronomical observation to reveal hidden truths about the universe. The ongoing Hubble tension, the perplexing discrepancy in the universe's expansion rate measurements, finds an indirect yet profound connection to neutron stars. While neutron stars themselves don't directly cause this tension, their role in forging cosmic distance markers, type E supernovae, which are thought to involve white dwarfs accreting matter from companion stars, and their potential as gravitational wave sources that can measure distances independently, means they are integral to the very cosmic scales being debated, also help refine our understanding of dark energy's influence on cosmic structure, as the equation of state for extreme matter impacts the evolution of the universe's largest structures. The very existence of neutron stars teetering on the edge of becoming black holes highlights the delicate balance of forces in the universe. It is a constant battle between the relentless inward pull of gravity and the quantum mechanical resistance of degeneracy pressure. This cosmic drama, playing out across billions of years and billions of stars, defines the ultimate fate of massive stellar remnants. They are the last bastions against the absolute triumph of gravity, a testament to the power of quantum mechanics to resist total collapse. Their breaking point, the Tolman-Oppenheimer-Volkoff limit, is a critical boundary in physics, marking the threshold beyond which even matter itself cannot maintain its form. Ultimately, the study of neutron stars and their exotic matter is not just about understanding distant collapsed stars, it is about understanding the fundamental forces that shape our reality. It's about quantum mechanics dictating the fate of astronomical objects, about general relativity revealing the true nature of space and time, and about nuclear physics explaining the very elements that make us. These objects challenge our intuition, redefine our concept of solidity, and force us to confront a universe far stranger and more extreme than our everyday experience could ever suggest. The echoes of neutron stars are all around us, from the precious metals we prize to the gravitational waves that ripple through space-time. They whisper secrets of creation and destruction, of quantum defiance and gravitational dominion. They remind us that the universe is a place of profound wonder and terrifying power, where the most extreme phenomena often hold the deepest truths about our existence. As we continue to probe these cosmic enigmas, we're not just accumulating facts, we're expanding the very boundaries of human understanding, revealing the universe's densest secrets, one impossible star at a time. Their story is a reminder that the cosmos is an endless source of awe, demanding that we constantly challenge our assumptions and embrace the truly bizarre nature of reality. Our journey through the realm of neutron stars has been one of profound extremes, a plunge into a reality where the very concept of matter is reimagined. We began with the cataclysmic stellar death of a colossal sun, its core collapsing inward with unimaginable speed, compressing atomic structure out of existence. This violent genesis gave birth to neutronium, a substance so dense that a single sugar cube of it would outweigh every vehicle on Earth. We then confronted the terrifying thought experiment of that mere teaspoon of neutron star matter unleashed upon our planet, a tiny speck of cosmic horror capable of tunneling through our world, initiating a global apocalypse and potentially consuming Earth from the inside out, reducing it to a silent, super-dense husk. We peered into the unseen depths of these stellar remnants, unravelling their bizarre layered interiors, from the iron crusts of crushed atoms to the superfluid oceans of neutrons and superconducting plasmas of the core, finally venturing into the speculative quantum soup of quark matter at their heart. These are not merely dense rocks. They are miniature universes where the laws of physics as we know them are stretched to their breaking point. Their existence is a delicate balance, a constant quantum struggle against the relentless, unyielding grip of gravity, a testament to the fact that even the most powerful force in the cosmos has a quantum counter. From these exotic interiors, we turned our gaze outward, learning how these invisible giants reveal themselves as cosmic lighthouses, pulsars spinning hundreds of times per second, whose precise rhythmic signals act as invaluable cosmic clocks and gravitational wave detectors, confirming Einstein's most profound predictions. Then, we witnessed their ultimate collaborative act of creation, kilonovae, the titanic mergers of two neutron stars. These events are not just explosions, they are the universe's grandest alchemical furnaces, forging the heaviest elements, including the gold, platinum, and uranium that are fundamental to our planet and our technology, an echo of their cataclysmic embrace, a direct connection between the subatomic and the astronomical. We saw how these objects stand on the precipice of ultimate oblivion, the Tolman-Oppenheimer-Volkoff limit marking the boundary beyond which even neutron degeneracy pressure succumbs to gravity, leading to the irreversible birth of a black hole. This transition represents the absolute triumph of gravity, transforming the densest matter into an ultimate vacuum, forever veiled behind an event horizon. Finally, we recognize neutron stars as indispensable laboratories, unique cosmic arenas where general relativity, quantum mechanics, and nuclear physics intersect, providing critical data for understanding the equation of state of ultra-dense matter and pushing the boundaries of human knowledge itself. The journey through the physics of neutron stars forces us to confront the sheer dynamism and often brutal elegance of the cosmos. Our terrestrial experience of matter is almost entirely governed by electromagnetic forces, the dance of electrons and nuclei that creates the solidity, texture, and chemistry of our world. But neutron stars exist in a different dominion, one where the strong nuclear force and gravity are the undisputed monarchs. The very idea that a teaspoon of matter could outweigh a mountain range challenges our fundamental intuition, making us realize how narrowly defined our everyday reality truly is. It is a profound demonstration that the universe operates on scales of magnitude and extremity that consistently humble our human-centric perspectives. This exploration also highlights the investigative rigor of modern astrophysics. We cannot visit a neutron star, nor can we recreate its core conditions in any lab. Yet, through painstaking observation of their light, their pulses, their gravitational whispers, and their cataclysmic mergers, we can infer their internal structure, their composition, and the very laws that govern them. It is an intellectual triumph, a testament to humanity's ability to decipher the universe's most cryptic messages, piecing together a coherent picture of the invisible and the unreachable. This detective work, relying on indirect evidence and complex theoretical models, is a powerful demonstration of the scientific method's capacity to unveil hidden truths. The implications of neutron stars extend beyond pure physics, touching upon our place in the cosmic narrative. They are part of the vast, intricate web of cosmic evolution that has led to our own existence. We are quite literally star stuff, but not just any star stuff. We are the beneficiaries of countless stellar deaths and a few neutron star mergers, elements forged in cosmic violence becoming the building blocks of life and consciousness. This realization imbues our existence with a grander context, connecting the fleeting moments of a human life to the billions of years of cosmic history. It is a humbling and inspiring thought, binding us irrevocably to the stellar crucible. Moreover, the frontier of neutron star research is still vibrant and full of unanswered questions. What is the precise equation of state of the matter in their deepest cores? Do they truly harbour exotic particles like strange quarks, or even more bizarre forms of matter unknown to our current standard model? Can we ever fully reconcile the quantum mechanics of the very small with the general relativity of the very massive within these objects? These aren't just academic puzzles. They are fundamental questions about the nature of reality itself, pushing our theoretical frameworks to their limits and demanding new insights, new theories, perhaps even a revolution in physics. Ultimately, the neutron star stands as a stark monument to the universe's capacity for extreme creation and destruction. It is a reminder that the cosmos is not merely a backdrop for human drama, but an active, dynamic entity, constantly forging new realities at the boundaries of what is conceivable. Its immense density, its quantum weirdness, its role as both a destructive force and a cosmic alchemist, compel us to look beyond our familiar world and embrace the extraordinary. The lessons learned from a single teaspoon of neutron star matter, however hypothetical, resonate with the deepest truths about gravity, matter, and the ongoing, awe-inspiring story of the universe. It leaves us with a lingering sense of wonder and a profound understanding that even in the seemingly empty vastness of space, there exist pockets of existence so dense, so powerful,